Hello, fellow chemists. Jolly here again. I would like to talk about ionic sizes in this specific mini lecture. And why do I care? Well, in the end, the sizes will determine the packing or the overall structure of my solids. And so it's very important to understand the different sizes and whether they're larger, they're smaller, so forth and so on. So I'm going to discuss ionic sizes. And first of all, how do you get the size of an atom? Okay, so that's where we have to start. How do we get the size of an atom? Oh, did that prompt anything? Long time ago, we talked about effective nuclear charge. ZEF. Effective nuclear charge. How well the protons are holding on to the electrons. How effective the protons are holding on to the electrons. Are they all made equal or are they not? And the answer is not. All right, so we have to consider, one, how far away they are. And this would be how far away the shell is. Two, we have to consider, well, how many protons and how many electrons are there? So we need to take into account the numbers of the protons and the electrons. And then finally, the effectiveness, or I'm going to call it interference. But we know it as shielding. Those outer electrons, do the inner electrons or the lower electrons, do they get in the way of them seeing into the nucleus? And so that is called shielding. So let's take an example here. I have my number of protons. And then I have, remember those are all in the nucleus. Oh, I better draw a circle. Okay, sorry, it's not completely spherical. But in this case, it's the nucleus. And then we have our electron shells. So n equals 1, n equals 2. Wow, that is such a terrible circle. All right, we've got n equals 1, n equals 2. And then I've got my wonderful electrons. So I have, and remember, they try and stay as far apart as possible. I have 2 electrons in the n equals 1, and then I can have a maximum of 8 in the n equals 2. So let's just put a few here. Okay, shielding is if one of these line up. So let's say I put one right here. Do you see it is getting shielded by this one? So it is not seeing the nucleus or the protons as much, and that would be considered shielding, so it has less of an effective nuclear pull on that specific electron. And that, of course, will then allow the electron to travel further out, and it will become a little bit larger than what we expect. So for the ions, here's your possibility. All right, if you have less protons in the nucleus than you do electrons. Now keep in mind, I cannot change the number of protons, but if there are less protons than there are electrons, then it gets too big and it expands, because the poor nucleus can't hold on to that many. Well, conversely, if there are more protons than there are, let's do a different color, let's do orange, and there are less electrons out here, well, it's going to shrink because the protons have more effect. They're pulling in tighter. So in a nutshell, cations are larger than their neutrals, and anions, I said that completely backwards, sorry. cations are smaller than their neutrals, and anions are larger than their neutrals. So this one right here, more electrons out here, this would be considered an anion. And this one right here, it has less, so this would be considered a cation. And remember, that is compared to the neutral atom. And that's how we would predict ionic sizes. All right, let's just do a couple practice problems here. All right, let's take chlorine versus chloride. Okay, well, let's look at chlorine. Okay, this is neutral, so I know, I'm looking at my periodic table right here, how many protons and how many electrons does neutral chlorine have? So from my periodic table, I should know this off the top of my head, but I don't. All right, so chlorine has 17. And let's put red. So plus, I want red. So a plus 17 in the nucleus. Now, where is it holding on to its electrons? It is in the n equals 3 shell. It's in the n equals 3 shell. And I know that, but I'm not so much interested in where, just the total. So I'm going to put negative 17 or 17 electrons. Okay, now let's compare that to the chlorine, which what does not change? The protons. But what is going to change? Instead of 17 electrons, it's going to have 18 electrons. So the 17 cannot hold on to that 18 as well as the 17 can hold on to the 17. So this one is going to be bigger. So the chloride, the anion, is larger than the neutral. Well, let's take a look at sodium. About sodium versus sodium metal. Okay, now sodium off the periodic table has 11 protons. So in its neutral state, oops, I wanted that blue. In its neutral state, it has 11 electrons out here. And here, okay, now keep in mind it's positive, so it's lost one, so it only has 10 electrons. So the 11 can pull that 10 in a lot easier than the 11 can pull in the 11. Excuse me. So this one over here is bigger. And this one over here would be smaller. So the sodium is smaller than the neutral. It's smaller than the neutral. Okay, now I didn't play with shells. So we're gonna jump into a problem and I'm gonna start swapping shells. Now keep in mind this is a ballpark. This is a ballpark. If you look up the actual radius somewhere, the actual number, it's gonna be close, but it might have a couple of variations. But this is a nice ballpark. Alright, so size, ion, and atom size comparison. I can't stress enough, this is a ballpark. You might make a prediction and then look up the actual numbers and go, oh, that's slightly backwards, but it's going to be close. It's going to be awfully close. All right, so let me make a list here. Let's see, who do we want to compare? Oh, I think we need to compare a neon, and we need to compare maybe a chloride, and oh, let's throw a chlorine in there, and an argon. Now I'm going to make this kind of long just so that there's a lot of examples. I'm going to throw in a potassium, and, oh, I don't know, a magnesium, and, helium, and helium. All right, so let's take a look. Now, the first thing I always look for is either the shells or the electrons, but because I know these have different shells, I'm going to look at the shells. So, neon, its shell is N equals 2. Chloride is N equals 3. And chlorine is N equals 3. Argon is N equals 3. Now, potassium started out in 4, but it lost a proton, or sorry, it lost an electron. So do you see it has dropped down to the 3? And then magnesium started out in the 3, but it has dropped down to the 2 because it lost 2 of the protons. And then helium is, of course, in N equals 1. All right, the next thing I want to talk about is the protons. And that is not going to change. So neon has 10, chlorine has 17, argon has 18, potassium has 19, magnesium has 12, and helium has 2. All right, now let's talk about electrons. Neon is neutral, so it has 10. Chloride has gained 1, so it has electron extra. Chlorine is neutral. Argon is neutral. The potassium has lost 1, so it's 18. Magnesium has lost 2, so it's 10. And helium is neutral, so it has 2. All right, now, in order to do in order to do sizes, we need to look at where they're located as far as shells. So let's see what I got here. I have somebody in the N equals 1. Is anybody else in the N equals 1? Nope. So that one's the smallest. Very close to its nucleus. Going to pull it in pretty tight because there's nobody in the way. In fact, helium is the smallest element on the periodic table because it has the most protons that you can have with N equals 1. So it literally is the smallest element on the periodic table. Okay, then I have let's see, it looks like an N equals 2. Is anybody else in the N equals 2? Oh ho ho, yes there is, so I need to do a comparison. So I have my neon. I have 10 protons pulling on 10 electrons. But over here I have what? 12 protons pulling on 10 electrons. So the magnesium is going to suck in tighter or shrink more than the neon. So the magnesium is going to be next. So let me start a little chart here. I am saying helium is the smallest, and then magnesium ion, and then neon. Okay, that takes care of N equals 2. Let's look at N equals 3. All right, so I've got U, and U. Whew, 3 of them. Or no, 4 of them. All right, so let's look at our protons. We've got 17 pulling on 18. We've got 17 pulling on 17. We've got 18 pulling on 18. Oh, and we've got 19 only pulling on 18. So this has the most protons, and it is only pulling on 18, so that's going to be the next smallest. All right, so that leaves us these 3. Oh, guess what? That has the next most protons, and it's only pulling on 18, so argon will be next. All right, and that comes down to my 2 chlorides. I have 17 pulling on 18 and 17 pulling on 17. Well, this is going to be the most effective, and so we're going to put chlorine and then chloride. So first I compared shell, and then I looked at the proton and electron ratio. And again, it's a ballpark. You know, we could look at these actual numbers and be really close, or, you know, perhaps maybe these two would have switched or something, but it gives us a great idea for overall atomic size. And so you should be able to compare and contrast neutrals, positives, and negatives now that you have seen the trends. All right, happy calculating. Jolly out.